So in the last class, we were talking about the Born-Oppenheimer approximation, the introduction to the Born-Oppenheimer approximation. There I showed how to constitute the Hamiltonian for a system with n nuclei and p electrons. You remember this, right? This is a Hamiltonian for a system with n nuclei and p electrons. Okay, and the first part of this Hamiltonian was the kinetic energy part for the nucleus, and the second term is for the kinetic energy of the electrons. And then we have the potential energy term. The potential energy term together is written as VRR, and we have defined the VRR. So this is the uh, here is the expression for VRR. The first term in VRR is the potential energy operator for the nucleus repulsion, and the second term is the potential energy operator for the electron nucleus attraction, and the third term is the potential energy operator for the electron repulsion. Okay, so now we have an idea about the Hamiltonian for this big system. And when we were discussing about various parts of the Hamiltonian, you know about the kinetic energy part for the nucleus, kinetic energy part of the Hamiltonian for the electron, and then we can write it as ENR plus dn electron plus VRR, plus then we rearranged this T electronic plus VRR in such a way that we together wrote these three terms, this one and this one, the first, third and fourth terms together as H electronic, because it deals with the electronic kinetic energy and potential energy. And the second term is the nuclear potential energy, nuclear repulsive potential energy interaction operator. Okay, so that one is written separated as Vn and R. So the first, third and fourth one together will constitute H cap electronic, and it is then added to Vn. That is T. That is the T electronic plus VRR. So that's what we said in the last class. Okay, and today we are going to use this Hamiltonian in the Schrodinger wave equation. So let us constitute the Schrodinger wave equation using this Hamiltonian. How to constitute the Schrodinger wave equation? Schrodinger wave equation is the eigenvalue equation of the Hamiltonian operator. So the Schrodinger wave equation is Schrodinger wave equation. Equation is H cap, okay, H cap psi is equal to E psi. I write E T psi, where T represents, T denotes total. That is the total energy of the system. Means the energy of all kinds, the kinetic and potential energy, okay, of the nucleus and the electron, everything together represents ET. So this is the Schrodinger wave equation. Now we can try to apply the Hamiltonian in this equation. Before that, we have to understand the nature of psi. So psi actually represents both the nuclear and the electronic part. Okay, so the psi in this equation can be written as psi is equal to, let me save some space, I will write it to the left. So psi is equal to the part for the electron, that is psi electronic, that depends upon R and R. You already know this, why it is depending upon RR because we have the H cap electronic RR. It depends upon the psi electron, the wave function of the psi depends upon the position coordinates of the electron, and also it highly depend upon the position coordinate of the nucleus also, because the electron is under the influence of the heavy nucleus. Okay, but the potential and the wave function part for the nucleus psi n, that depends upon the position coordinates of the nucleus alone. You can define the entire system of the nucleus with the nuclear coordinates itself. You don't need to depend upon the coordinates of the electrons around it. Okay, so we can express psi as psi electronic RR into psi n R. Okay, so what we are going to do is we are going to substitute for psi, substitute psi and h cap in our Schrodinger wave equation. Psi and h cap in the Schrodinger wave equation. Okay, this is a Schrodinger wave equation. H cap psi is equal to H psi. So we are going to substitute this in the Schrodinger wave equation. Then the Schrodinger wave equation becomes, what is h cap? We already have h cap as minus sigma is equal to sigma I is equal to 1 to n, that is that we are writing the kinetic energy part for the nucleus, h square divided by 8 pi square mi, capital Mi, del I square. Okay, that is a kinetic energy operator for the nucleus, minus sigma j is equal to 1 to p, j is equal to 1 to p, h square divided by 8 pi square m del j square. Okay, that is the kinetic energy part of the electron, then plus VRR, right? VRR. That is the potential energy of the system. VRR. Then psi. What is remaining is psi, right? Psi is psi electronic RR and psi nucleus R. Okay, psi RR is equal to ET into psi. Psi is psi electronic RR psi nucleus R. Okay, psi and R. So this is the Schrodinger wave equation. So let me put some number for this equation. What was the last number? Okay, 1, 2, 3. Then we have this equation. Let me put this as equation number 4. Then this is equation number 5. Okay, so this is equation number 5. So we have the Schrodinger wave equation, and now we can again expand the Schrodinger wave equation. So for that we have to carry out the partial differentiation, right? So on carrying out the partial differentiation, we have del I square operating over psi electronic RR psi n R. See, del I square, this one, this del I square operating over this function psi electronic RR psi n R. So we will solve that first. Okay, so let us get what is the expression for that. Del I square psi electronic RR, then psi n R is equal to, we can write it as del square is del I square is equal to del I dot del I. You already know this, right? What is del I and del square? Del under del square. Del is I dou by dou x plus j dou by dou y plus k dou by dou z, and del I square is dou square by dou x square plus dou square by dou y square plus dou square by dou z square. Okay, so this is del I, then psi electronic R psi n r, we can write like this, right? So that is equal to del I to operate the del I. In quantum mechanics, we are doing this operation from right to left. So we have to operate the function inside the bracket with the operator on the right side. This is operator on the right side. So we have to operate the function inside the bracket with the del I, okay, and then operate that with the other del I. So that's what we are going to do. So this del I here, the del I here outside the bracket here is the first del I which is written here. So then we have to write inside the bracket what was the expression after operating this function with the right li. Okay, so inside the bracket we have first function into the del I of the second function. Okay, actually it is first function, that's a derivation, which is a partial differentiation. And so partial differentiation. So first function, that is psi electronic R, the differential of the second, that is del I psi n r, okay, psi n r, plus second function, that is psi n r into derivative of the first, that is del I psi electronic R, okay, that is equal to, now again we have to derive both the terms inside the bracket with the del I term, which is outside, del I is outside the bracket. So we have to apply del I on both terms, first and second terms inside the bracket. So let us do for the first term. Then the first function, that is psi electronic R, the derivative of the second, that is del square psi n r, del I square psi n r, plus second function, that is del I psi n r into derivative of the first, that is del I psi electronic R, okay, derivative of the second. Then we have to do it for the second term here, So the second, when we are doing it for the second term, then we get plus first function, that is psi n r into derivative of the second, that is del I square psi electronic R plus second function, that is del I psi electronic R into derivative of the first, that is del I psi n r, okay, psi n r. So we have to simplify this further. Here we have to understand that del I and del I square refer to differentiation with respect to the r only, because del I and del I square represents the del I and del I square operates over the nuclear coordinates. You know this from the Hamiltonian. You look back at the Hamiltonian. See, this was the Hamiltonian, and del I square is here. That is the first part of the Hamiltonian, right? So del I square, here the del I square is the Laplacian operator for the nucleus. Okay, nuclear kinetic energy. So This Laplacian operator operates over the position coordinates of the nucleus. The position coordinate of the nucleus is represented by capital R. So in this expression also, wherever we have used del I, okay, and del I and del I square will operate only over the capital R only. So that is very important. Del I and del I square, del I and del I square operates over R only. Okay, and now what we have to do next is, now we are going to bring the Born-Oppenheimer approximation. That is very important. Born-Oppenheimer approximation. So I am going to state what is Born-Oppenheimer approximation. Here we are going to the central part of our discussion. Born-Oppenheimer approximation. It's a central part of our discussion. And from Born-Oppenheimer approximation, we have to consider that it's actually a simplifying approximation. Okay, that the nuclei are much heavier than the electrons. That is the first assumption. Nuclei are much heavier than the electron. Nuclei are much heavier than the electrons. Nuclei are much heavier than the electrons. And then what is the consequence of that? Since nuclei are much heavier than the electrons move faster than the nuclei. Electrons move faster than the nuclei. Faster than the nuclei. Okay. So this is the Born-Oppenheimer approximation. In other words, nuclei are considered as fixed. This is equivalent to say that nuclei are considered as fixed. Nuclei are considered as fixed when electrons carry out the motion. When electrons carry out the motion. Electrons carry out the motion. Okay, so this is the important Born-Oppenheimer approximation in words. Okay, so in classical terms, you can consider like when the electron performs one complete cycle. You can consider that the change in the position of the nucleus during that complete cycle of the electron is almost negligible. Okay, when electron moves around the nucleus, for example, during when the movement, if you're looking at the nuclear change in position, that change in position is negligible. So when compared to the electron, you can assume that the nucleus is at rest. This has very, very, very big advantage in simplifying the calculation. For example, you can consider yourself as traveling in a bus. Okay, you are traveling in a bus, and when you are traveling in a bus from Trivandrum to Cochin. Okay, so you are in a bus. And you are traveling from Trivandrum to Cochin. So after some time, you will reach. Your bus will reach Cochin. Okay, Cochin. So you are traveling this distance, and you are inside this bus. The driver is there, you are there, and some other people are there, and then you are traveling this closed bus. And you suppose that you are sitting when the bus starts from Trivandrum. You are sitting just behind the driver. Okay, after some time, think that it is not a good position to see the watch the TV just by sitting just behind the driver, and then you choose to go to the back seat and then watch the TV in a much better way. And so you move from one position to the other position of the bus. So, in order to describe your position in the bus, we have to depend on some coordinates, right? So we have to depend on some coordinates. Suppose that your coordinate system has an origin at the Trivandrum bus station. Okay, so your coordinate origin is here. Your x, y, z coordinate origin is here in the Trivandrum bus station. Okay, and then you are moving from Trivandrum to Cochin, so that your x, y, z coordinates are keep on changing, right? So your x, y, z coordinates are keep on changing, and in order to track that change, what you can do is you just track the position coordinates of the steering of the bus, right? Then it will say that it will give the position coordinates of the bus, for example, at a particular point of the bus. But when you are traveling inside the bus, okay, the position coordinates of the steering uh, will not describe your position coordinate, even if you are inside the bus, because compared to the steering, you are making again some other movement from back to front, front to back, something like that. Therefore, the position coordinates of you and your bus, okay, that is actually not in pace with the movement of the bus. Okay, the position coordinates of the steering is changing, uh, changing as the bus moves, but that is not enough to describe your movement, because your position coordinates are changing when the bus is moving from Trivandrum to Ernakulam. That's happening already. But again, your position coordinates are changing because of your internal movement inside the bus, right? So that the systems, in order to describe your position coordinate, it's a very complicated stuff. It is not enough to describe the movement of the bus. That's not enough. And inside the bus you are moving, so for describing your position coordinate become even tedious. So that is what is actually happening inside the molecule also, because suppose the nucleus is moving, okay, nucleus is moving, and with respect to the nucleus, the electrons are also moving. So if you are considering the kinetic energy of the nucleus and the kinetic energy of the electrons together, then all things will be a bus at the end. Likewise, you consider the kinetic energy of the bus, and then the kinetic energy of the bus and the kinetic energy of you were different because you were moving inside the bus. Like that, it will be a complete mess. So this system is going to be very, very complicated and tedious. So we need some simplification. Right? So in order to do that, what we can do is just to understand your movement, we can do one thing: keep the position coordinates, the origin of the position coordinates at the front of the bus or at the steering of the bus. Okay, if the position coordinates is at the steering of the bus itself, okay, the origin of the position coordinates will move as the bus moves, or with respect to the origin of the position coordinate, the steering is at rest, right? If you are fixing the position coordinate at the bus stand, Trivandrum bus stand, then the bus will be in the movement, because the position coordinates describe the steering of the bus will keep on changing. But if that or system, the coordinate system, is fixed at the steering itself, then the steering is not moving, right? With respect to the coordinates, the x, y, z of the steering are not changing when the bus is, even if the bus is moving. Then if you are fixing the position coordinates in the steering itself, then it is easy to describe your motion, right? It is easy to describe your motion, because the movement of the bus doesn't affect position coordinates. Your position coordinates will be affected by your motion only if you are fixing the coordinate system in the steering itself. So what we are doing here is that we are keeping the bus, we are considering the bus as fixed. Okay, even if the bus is moving, we consider the bus as fixed by keeping the position coordinates in the bus itself, by fixing the origin of the position coordinates in one part of the bus itself, so that the bus will be considered as in rest, and then your movement only will be counted. Okay, so that the arrangement of the people inside the bus can be described in a much better way if you are considering the coordinate system like this. So somewhat similar approach only we are doing in the case of the electron nucleus system also. You consider the nucleus is fixed. Nucleus is fixed, and once the nucleus is fixed, what is the movement of the electron around the nucleus? That is going to describe the structure of the molecule. Okay, that's what we are going to do. Okay, then that approximation is called the Born-Oppenheimer approximation. So we stated this approximation in words. Now we are going to apply this approximation mathematically in our Schrodinger wave equation. Okay, so that's what we are going to do next. Now we have the Schrodinger wave equation. In the Schrodinger wave equation, we have expanded one term, del I square psi electronic r psi n r. That is what we have expanded here, right? And because of this approximation, now from the Born-Oppenheimer approximation, the changes in the psi electronic RR due to changes in R are negligible. Okay, that is very important. Due to Born approximation, the changes in psi electronic RR due to changes in R are negligible, right? Negligible. Okay, so this is negligible. So why it is negligible? Because R is the position coordinate of the nucleus, and you are thinking that the nucleus is at rest, means the change in the R does not have any influence in the movement of the electron, because electron is moving much faster than the nucleus. And while the electron is moving, you can consider the nucleus as fixed. Therefore, the negligible change in R is not going to bring any effect in the electronic wave function. Therefore, changes in the psi electronic RR due to change in R are negligible. That is the mathematical implication of the Born-Oppenheimer approximation. Okay, so wherever you operate these del I or del I square with psi electronic RR, those terms will become 0. So what is the mathematical consequence of this one? Del I psi electronic RR, del I psi electronic RR will be approximately equal to 0. Not only that, del I square psi electronic RR will also be approximately equal to 0. This is a mathematical implication of the Born-Oppenheimer approximation. Okay, so when these terms are becoming 0, now you look back at our expression. So wherever you see these terms which is equal to 0, those terms will be vanished from our expression. So here psi electronic RR, psi I square psi n r, nothing is there to be vanished. But here you look at here we have psi electronic RR, that is equal to 0. So the second term will be vanished. Here also we have psi I square psi electronic RR. So that term will be vanished. Here also we have psi electronic RR. So that term will also be vanished. So in this expression, only the first term will exist. All other terms will be vanished. All other terms will be vanished, right? That is the consequence of the Born-Oppenheimer approximation. So now we can write simply that del I square psi electronic RR psi n r, del I square del I square psi electronic R psi n r is equal to only the first term. What is the first term here? The first term is psi electronic psi del I square psi n r. Psi electronic del I square psi n r. Psi electronic del I square psi n r. Okay. Now this is the simplest expression. Now in the equation number 5 is a Schrodinger equation. Okay, in this equation now we are going to find out del J square psi electronic r psi n r. Del J square, because we have del J square here, and del J square is operating over psi electronic r psi n r. So we are going to find out the value of that. Del J square psi electronic r psi n r. Okay, so this is what we are going to find out next. Del J square psi electronic r psi n r, and you can see that the del J square operates only over r. Del J square only operates over r because that was the Laplacian operator for the electronic coordinates, right? You may be remembering from the Hamiltonian. Del J square. See, this is the del J square, and this was the kinetic energy part. The second term was the kinetic energy operator for the electron, and here the del J square is the Laplacian operator for the electronic movement, okay, or electronic position coordinates. So del J square will operate only over the electronic position coordinates. Okay, so what we can write here is psi n r that we can take out, because that is the J square is not going to operate over this function psi n r. Then what is remaining is del J square psi electronic r. Okay, psi electronic r. So we have two expressions here, and let me give some numbers for this expression. Let me give this one as 6. Okay, then this as 7, this one as 7, and this one as 8. Okay, now what we are going to do is we are going to substitute these 7 and 8 in our Schrodinger equation. Okay, Schrodinger equation was equation number 5. Okay, so we are going to substitute 7 and 8. Substitute 7 and 8 in equation number 5. Equation number 5 was a Schrodinger equation. So let us substitute. So what is that? Equation number 5. Okay, this is equation number 5. So the equation number 5, we have minus sigma I is equal to 1 to n h square divided by 8 pi square mi del I square psi electronic r psi n r. Okay, that we will write first. So minus sigma. So you have to write all this in your notebook, otherwise you cannot follow. Okay, then you have to check back what is written in the previous page, because I can't show all the things written in the board here. Okay, so when we are substituting 5, we have minus sigma I is equal to 1 to n h square divided by 8 pi square mi, then del I square operating over psi electronic r psi n r, that is equal to psi electron. We already have the expression for that. That is the expression 7. So we can substitute that there. That is psi electronic r del I square psi n r, del I square psi n r. Okay, so that is the first term in the Schrodinger wave equation. Now we have to go for the second term. In the second term, we have the kinetic energy that represents the kinetic energy of the electron. So we have there minus sigma j is equal to 1 to n. J is equal to 1 to n h square divided by 8 pi square. H square divided by 8 pi square m. Then we have del j square psi electronic RR psi NR. We already have the expression for that, right? The expression is in equation number 8. So we will substitute that here. Then we have psi psi NR, del J square psi electronic RR. Okay, so we substitute that there. Then what's remaining in the Schrodinger wave equation? So these are the kinetic energy parts. Then what's remaining is the potential energy part. That is VRR, that is the potential energy, VRR into psi electronic RR psi NR. That also we have to write. So we have to write the potential energy part, that is VRR plus VRR, and let me write it here, plus VRR, okay, psi electronic RR psi NR, psi electronic RR psi NR, okay, so that is the potential energy operated over the wave function, okay. And that's equal to, that is the left hand side of the Schrodinger wave equation. Now that's equal to right hand side. In the right hand side we have the total energy ET multiplied by the wave function. The wave function is psi electronic RR, psi NR. Okay, so that is the right hand side. Now what we are going to do is we are going to divide the entire equation with the psi electronic RR psi NR. So that's what we are doing. Divide by psi electronic RR psi NR psi NR. We're going to divide the entire equation. Not only we are going to divide, we are going to rearrange after dividing also. So dividing and rearranging. So let us divide the first term, and we will divide all the terms, but the first term will be taken over to the other side. Okay, means the first term, the left hand side, will go to the right hand side, so that its negative sign will become positive sign, so that we can write sigma I is equal to 1 to n, sigma I is equal to 1 to n, h square divided by 8 pi square mi, h square divided by 8 pi square mi. Okay, then we have to divide this with psi electronic RR psi NR, so that psi electronic RR will be cancelled from the numerator. So what is remaining is del I square psi NR divided by psi NR psi NR. Okay, so this term has gone to the right hand side. That's why its negative sign has gone. Then what is remaining in the right hand side, that should be added to this one. So that is equal to ET into psi electronic RR psi NR divided by psi electronic RR psi NR, so that only ET will be remaining there. So that is ET. So that is equal to minus what is remaining here, minus sigma j is equal to 1 to n, j is equal to 1 to n, h square divided by 8 pi square m. Then this psi NR del j square psi electronic RR divided by psi electronic RR psi NR, then so that psi NR will be cancelled from the numerator. So what is remaining is del j square psi electronic RR divided by psi electronic RR psi electronic RR. Okay, plus VRR plus VRR. Okay, so because VRR psi electronic RR psi NR, that is divided by psi electronic RR psi NR. So remaining is VRR. So we have this equation here. Now you look at this equation. In this equation, if you're looking at the right hand side, that is a differentiation of psi NR, okay, psi NR with respect to the Laplacian operator for the nuclear coordinates. Okay, and here what you can do is the differentiation with respect to the electronic the Laplacian operator in terms of the electronic coordinates. So we are doing the differentiation both sides, but the differentiation is with respect to different coordinate systems, and that means that both sides of the equation will be equal to a constant. This will be equal to a constant. We have done this type of steps previously also. This will be a constant. Let us say that this constant is u, that is equal to u. This constant is equal to u. So now we can create the two new equations, because both the left hand side and the right hand side of the equation can be equated to u. Okay, so let me give an equation number to this one. 8 next equation is equation number 9, right? So this is equation number 9. From 9 we can create two new equations, right? Left hand side and right hand side is equal to u, so we can create again two new equations. So now let us create the new equation. Again, 40 minutes are over, I will explain the rest of the things in the next class. 40 minutes are over, so let me put an end to the lecture here. Okay, so we will see the next things in the next video.